All right. Acid-base titrations. All right. Can anybody give me a definition of what a titration is? You've done them. You did it in Chem 11. We've done 2 of them in Chem 12. What would you call a titration? An acid-base neutralization. It doesn't have to be acids and bases. All right. The ones that we do now are acids and bases. You'll see later on we'll do a redox one. Okay. Redox chemistry just means you're changing electrons. And you can do a solubility one, which I'll show you later on as well. Okay. So there's different ways, but I understand what you're saying. It's basically if you want a proper definition, controlled reaction leading to a quantitative endpoint. They're used to measure how much something is there, basically. That's why it's quantitative. Okay. Now, in this unit, obviously, it's an acid-base reaction. We've already done that using NaOH. We have a burette. We've all know how to use a burette, I assume. Measure the beginning point, measure the end point, subtract them, you know how much you added. In acid-base titrations, we use indicators, which basically just tells you when you've reached the equivalence point or the end point. Okay, hopefully those are the same thing. They are not always the same thing. Okay. And there's lots of different indicators. We'll see some of those. We do a lesson on indicators in here and how to pick the right one. So indicators are just chemicals that change color depending on the pH. That's why we use phenolphthalein, because when it becomes basic, it turns pink. That's it. All right. The transition point, also known as the end point, is when the indicator turns color. Okay, so in all the ones we've done, it's when it goes pink. Some people it's light pink, some people it's dark pink. Okay. And then there's the equivalence point. The equivalence point is when the moles of reactants and the moles of the titrant that you're adding are equal to each other. Okay? It is not always the same as the transition point, as you'll see later on. Okay, so if we have a acid in solution and we're adding our base, say it's NaOH, when these two things are equal, that's the equivalence point. That's what we're trying to get to. And ideally, you want your equivalence point and your transition point or end point to be the same. But it doesn't always work out that way. But you can get close. Okay? And that's what this bit says, is just talking about how you want them to be the same, but it can't always get there. All right. Standard solution. This is the solution that is in the titrant that we standardize the NaOH. We know, is in the burette. This is what we know. We know the concentration. For example, when we did our NaOH one, the concentration of NaOH, we had anywhere from 0.485 to 0.495. Okay. So that's what we measured using the oxalic acid. Why did we use oxalic acid and not just rely on the NaOH? Thank you. So the water absorption, right? NaOH absorbs water from the atmosphere. It becomes heavier. So when you weigh out 5 grams of it, you don't actually have 5 grams of NaOH. You have 5 grams of NaOH and water. So it's more of a diluted form. That's why when you measure the concentration of, say you wanted 0. Why am I putting brackets from that? You say you want 0.5 molar and you weigh out enough for 0.5 molar, your actual concentration is always going to be slightly under, right? Because you put water molecules into it. So it dilutes out the sodium hydroxide. Okay, what can we use titrations for? Or sorry, how do we do them? So, first thing, we know that we've already done this a bunch of times, so this should be straightforward. 0.5 molar NaOH. You don't have to draw this. I add it into the beaker, or the Erlenmeyer. You add a known amount of that solution so you know the number of moles of the standard that you used. So step one is determine the moles of standard. So say I add 10 moles of NaOH. Say this is my reaction. HX plus NaOH goes to, we'll say, come on. Say H2X. Goes to Na2X plus water. So you have to balance it, right? Okay. How do I figure out how many moles of H2X there are for the reaction that I wrote there? What's the key? What are the key numbers here? Yes, it's all about the coefficients, right? That's a 1, that's a 2. So you need 2 moles of NaOH to neutralize 1 mole of H2X. Okay? So unknown, I'll just say H2X. Using the balanced reaction. So you always need a balanced reaction. And then you can determine the concentration. Because you measured the volume, which is why on that lab, when I asked you, why does the actual volume not matter? Like you could change the number, 5 mils, 10 mils, 12 mils, 7.3 mils if you wanted. As long as you know the volume of the unknown that you added, you know you can figure out the concentration from there because you know the number of moles. And it also is the reason it doesn't matter if there's water in the beaker because the number of moles don't change. All right. And that should say step 4, I guess, or step 3, I guess. I guess it's the same thing. Or you can calculate percent purity, which is kind of what we're going to do this week with the aspirins. All right. Which is the pure weight over the impure times 100 to get percentage. All right. Let's just do a couple of calculations. This is a super short lesson, so we're just going to do a couple of calculations, and then I'll give you some time to work. So we have a volume of 23.5 mils of standard 0.135 molar sulfuric acid, H2SO4. We titrate 50 mils of NaOH to of unknown concentration to determine the concentration of NaOH. So what's the first thing we need? You need the equation. So H plus H2SO4 to neutralization reaction. So you form a salt, Na2SO4, and 2 moles of water. And I need a 2 in front of the NaOH. All right, what now? Moles of what? Yeah, so this is our standard. We have 23.5 mils of 0.135 molar sulfuric acid. So that's how much we added into the Erlenmeyer. So the moles of H2SO4 is going to be amount of liters, 0.0235 liters times 0.135 molar. Chickens. All right, so that gives us 0.00317 or 3.17 times 10 to the minus 3 moles of H2SO4. How many moles of NaOH do we have? 2 times that, right? Because it's a 2-to-1 ratio, right? 1 mole neutralizes 2 moles of that. Therefore, moles of NaOH. I don't know what I'm saying right now. I'll do this. One mole of H2SO4 neutralizes 2 moles of NaOH. That's what I wanted to say. So basically multiply it by 2. 6.35 times 10 to the minus 3 moles of NaOH. Just 0.317 times 2. Okay. Sorry, I carried the decimals. You're right. 634 moles of NaOH. And then divide by the volume to get the concentration. So the concentration of NaOH. This is basically what we've done for the last couple of labs. What's the volume? 0.050 liters gives me 0.127. Yeah? All right. When you do your calculations, people, I want to see the units written out like this. Like I said before, people just gave me this stuff. Some people, not everybody. I just got that without the moles. Okay? You got to write the units. All right? Otherwise, it doesn't mean anything. All right. Last question. Percent purity. We have an impure sample of oxalic acid weighing 0.581 grams, titrated with standardized 0.287 molar NaOH. 23 mils of NaOH are required. Determine the percent purity of the sample. What's the first step? Equation. I mean, depending on what you want to do, but we will need an equation. So, oxalic acid, we're going to write it slightly differently. H2C2O4. There's the balanced. So it's going to be the same, all right? Because when you titrate it, the NaOH is going to neutralize all the oxalic acid. So we're going to figure out how much oxalic acid we have. So the moles of NaOH that we add is going to be 0.287 molar times the 23 mils, written in liters. What's the ratio? 1 to 2 what? Yeah, so every 2 moles of NaOH are required to neutralize 1 mole of oxalic acid. So this time we're dividing by 2. So 2 moles of NaOH is 1 mole of oxalic, which gives us 3.30. So we got the moles of oxalic. How am I going to figure out the percent purity? We started with 0.581 grams. We got 3.3 times 10 to the minus 3 moles. What do I need to do? Yeah, so I got to convert the moles of oxalic acid into grams. I'll tell you, the molar mass is 90 grams per mole. Which gives you 0.297 grams of oxalic acid is how much was in the sample. The original sample weighed 0.581. So how do I figure out the percent purity of it? There you go. You just divide them. Times 100 gives you about 51.1%. Not very pure. It's half, well, depending. All right. That's the kind of thing you're going to do on Wednesday. All right. You're going to basically figure out how pure or how much of the pure aspirin, the acetylsalicylic acid, is in one tablet. Okay. So you're going to break it up. You have to do a couple things to extract it and then titrate it. The titration is yeah. Okay, are there any questions? Yes. Why is this the pure? Because, okay, so that's a good question. We are assuming that the other stuff in there does not react. It's unreactive. Okay, so only the sodium hydroxide only neutralizes the oxalic acid. It's the only thing it'll react with that is in there. So this is the reaction. You know you added however many moles of this. If the only thing it can react with is the oxalic acid, then this has to be just pure oxalic acid.
So the 0.581 grams is just the weight of something that has.
That's like you reached into. It's sort of like the sodium hydroxide. Yeah. It's a artificial weight. It's not a pure weight. Okay. It's like you took it out. Yeah, exactly. We're just saying none, but you have to assume none of that stuff participates in the reaction. Because if it does, then you're way off. Okay. And that's what happens with aspirin as well. But I'll talk more about that tomorrow. All right. Rest of the package, please, people.
Is the pure weight always
Should be, yeah. Yeah, because otherwise that wouldn't really make sense. You'd have over 100% pure. So, yeah. Yeah, total weight. Mass of the whatever thing. Sorry? Sorry.